All right, we are working on a diffusion problem that concerns nitrogen in a sheet of steel. And so we have a sheet of steel, and I'm going to, the reality is we have a sheet of steel that has a cross-sectional area, right? But I'm going to be kind of just drawing it head on so that I'm drawing kind of that line and that line. And so for my sheet of steel, what we will see is that if we have distance increasing in this direction, we are at a distance of 0 on the left-hand edge, and when we get to the other side of the piece of steel, we are at a distance of 3 millimeters. I'm going to call this distance. And then if I record the concentration of nitrogen, we see that the concentration of nitrogen in the steel at the high pressure surface is 4.7 kilograms per meter cubed. So if I call this the high side, high nitrogen, what this problem is telling us is that at the high nitrogen side at the surface of the steel, it's 4.7 kilograms per meter cubed. So it's going to be diffusing down to some lower value over at the other side of the steel that we're not actually given. And the question is then asking us, how far into the sheet? In other words, what distance, at what distance in the sheet from the high pressure side? So if I pick a point and I call it X, so at what point X in the sheet will the concentration be this lower value of 2? So let's make that be 2.0 kilograms per meter cubed. And so I'm going to kind of like draw sort of the whole thing. So again, we don't know that. We don't need to know it. Doesn't matter. But we are given this one's concentration is 2 and this one's concentration is 4.7. So we're if we make this point A and this point kind of B, and we start thinking about our concentration gradient, or we can approximate that as delta C over delta X. The way you do that is you take the concentration at one point, subtract it from the concentration at the other, and then you do the same thing with the distances, but you've got to make sure that your B points are always on the same side of the equation. And so what we get when we do this is we get 2 minus 4.7 over X minus 0 units of kilogram per meter to the fourth. So we see that the concentration gradient is minus 2.7 over X, and this will be in units of kilograms per meter to the fourth. So that is our dc dx. So why did I do that? Well, I can definitely see a need for Fick's first law to be applied. And Fick's first law says that the flux, right, is equal to the diffusivity, or the diffusion constant, times dc dx. All right, and let's go back and see what we're given. We're given D is 6.5. So I can just go on and start writing this. Minus 6.5 times 10 to the minus 11 meters squared per second, times, the dc dx that we've already worked out, minus 2.7 over X, kilogram per meter to the fourth. And that's going to equal the flux, which we are also given. Look. So that will equal 1.3 times 10 to the minus 7 kilograms per meter squared second. So I'm going to put, this is the equality. We have 1.3 times 10 to the minus 7 equals the product of those two negative numbers. And there's only one unknown in it. And so we can solve for X. So I'm gonna solve for x in this equation, and I will see that x is equal to, the two negative signs cancel each other out, so I will have a positive, what will I get? Positive 6.5. I'm doing a lot of steps in my head, so if I'm going too fast, you can do it a little slower on your paper. We will have a 2.7. We will be dividing by 1.3 times 10 to the minus 7. And when the units all work out, we kept ourselves in meters, right? So we're all good. Kilograms cancel out with kilograms. And so we will end up with an x in lengths of meters, and it ends up being 0.00135 meters. So that is our final answer. At a distance of x of 0.00135 into this block, right? We will hit that concentration. And if I turn that back into millimeters, that's 1.35 millimeters. And I'm really happy to see that it's less than 3, because the answer should be somewhere within the steel plate. So the answer makes sense, and we're good. All right, thanks very much.